L is prime, Q a power of P, and Q is equivalent to 1 modulo L, but not modulo L square. Compute set of T for the number of solutions, roots of unity, to a fixed power of L in FQ to Rth. I think it's time for an example to get a grip of what's happening here. So L it doesn't work. I have to change layer. Example, L equals 3, P equals 3, not a good idea, 5, and Q equals 5 squared, which is 24 plus 1, and 9 fails to divide 24, so the prerequisites are fulfilled. Now, N1 is the number of solutions to the equation. Actually, we have to choose an M. Let that be 1 for the time being. And that's for X in FQ. So the multiplicative group here has 24 elements. And it's cyclic. And L was 3, so we have to look for roots, cubic roots of unity, and there's unity itself, and then the 8th power and 16th power of a generator. So we have 3 of those. And 2, that's the number of solutions to the same equation. X to the 3rd equals unity for X and FQ squared, which is F5 to the 4th. And we have 3 all the way through here. All right, that was one example. Now let M be 2. That was M equals 1. M equals 2. That's X to 9th equals unity, X element in F25. And that's 24 is the order of the multiplicative group, so that's 3 again. Now when we go to N2, we are in F625. Now that's 3 as well, because 9 doesn't divide 624. So in that case, whatever m will be, I guess we will have 3 solutions. We will have 3 because 3 divides any power of q minus 1, and no higher power does, no higher power of 3. So we have to prove that. So that's a claim. In this case, 3 will divide, but 3 squared won't. I need to make a toilet break here. We can factor this. Why isn't this r? This should be r to make any sense of it. Well, leave it. Of course, L divides this exactly 1 time. So the condition is, does L divide this sum? Well, they are all equivalent to 1 modulo L. Now, how do we write that? The remainder with respect to L so that's n minus 1 times the remainder of q to any power which is unity. And that means if so n minus 1, if that's 4, so we have to do all the examples to make sure that my reasoning is correct here. So I'll need the phone to get the exact numbers, because I want to check this. I don't want to repeat thinking the same way. For some reason, you couldn't see my working on Maple, so I've just inserted it here. We wanted to factorize different powers of of 25 minus 1. And we wanted them for I equals unity to say, well, let's see if we can do 20. We could. And I'll just make it a little larger for you better to be able to see it. So first we have factor 3 to the first and then to the second, then twice to the first, then to the second, then twice to the first, and then to the third. And the next time we'll get to the fourth, that will be when we come to 27, and I don't think we can ask Mabel to do that. Let's try. We certainly could, and we got 3 to the fourth. So we have to make a system here. The number of terms, when it's a power of, I didn't quite get this, by the way, when it's n to the third, then we should only have 2 terms adding. No, it's 3. It's also 1. I forgot that we count from naught. And that means that we have n addends. And terms in the sum. So it's just the power of L dividing n, and that was R, of course, dividing R. And that goes all the way up to L to mth. This turns out to be a little more complex than I anticipated. If m is 2, or let's say m equals unity, then nr equals L. If m is a square, then LR equals L or L squared, depending on whether L divides R. And if m equals 3, then nr is L to the third. If L squared divides R, L to the second. If L exactly divides, and otherwise L. My. And then we should compute the L function. In a systematic way, we start with the L function for a constant L, and then we make the L function, the Z function, sorry. We start with the Z function for nr is constant. Then we add, and have to multiply, of course, the Z function for L squared minus L, in case L, when R is a multiplum of L. And then we just substitute that for L squared and then add up. Then we see what we get. All right. And then the m equals something. Oops. Then if nr equals naught and then something, say unity, for r is a power of, was it a power of L? Yeah, a constant times the power of L. That is R divides L. We just take, no, we could generalize it immediately. L to some power, n, and not when it doesn't. Yeah, should we? Yeah, let's write it up, all of it. And then we let R be I times this guy. So it's ln divided by IR, t to IR, I have no idea what to do with this. Oh, we can just let it be a sequence with now where did that L to the nth come from? R is a power of, so it's times, I don't know where I had my mind. First, the value divided by R, the R value, which is I times L to nth, and then T in I L nth. And we write it as one divided by lnth we take out, and then it's t in lnth to ith power divided by I. And that's the pth root, and this sum becomes 1 divided by t to L to the nth. So it's 1 divided by the pth root that's ridiculous. It's L to the nth root L to the nth root of 1 minus t to L to the nth. And if we put another constant here, as we will, we can just as well do that, a, then we get a here, and then it's the, then we can just make it as a power. I think that would be a better idea. L to the nth. We don't have room for that there. And the power is a divided by L to the nth. So let's try m equals 2 now. We have to add L squared minus L when L to the first divides R. That means that A is L squared minus L. We take the first one, and then we add and A was L squared. What was that? L squared minus L. Divided by L squared. That was the power. Minus t to L squared, and then L squared minus L divided by L squared. And of course this is not a rational function, because this gives unity and 1 divided by L squared, so we have to take a root of this. And of course this isn't a square or anything, so no problem there. And in case m equals 3, it doesn't seem logical that it's not t to the lth. And then that becomes L to the third minus L squared divided by L to the third. Oh, that gives the same. So they can be put together if one wants to. I think I've made a mistake when adding up the constant here. I can't see it though. All right. So generalizing this should actually solve the problem, if I'm right. Let's see if we can take on the second part. The one for which there is a solution for some m, the number for which it works for some m. I need a break, and my time is up, so I will continue recording some other day. Bye for now. Editing the video, it appears that part of the recording or part of the work I failed to record. So I'll just do that again. I felt something was wrong. Actually, I thought that Weyl's theorem implies that these set functions were rational, all of them. So this is a little weird. And then it felt wrong that we went from 1 minus t to 1 minus t to L squared, whereas the 1 minus t to the Lth. That was weird. And then just when watching it now, I realized that this was wrong. It must of course be ln divides I, ln fails to divide R, ln divides R. And then, sorry, the next thing was that if n is unity, then the number of solutions is L squared, and we need to subtract the L we already had. Now going down to m equals 2, we get A here is then L to the second minus L, and n is unity, so it must be divided by L, and that means we get 1 divided by t to the Lth to the L minus 1. This is the guy. So this is wrong. And now when m is 3, we have to add this with 1 minus t to L squared, and then this will certainly become L minus 1 once again. We are left with problem 6b. When we have the number of solutions, for any m, then we just need to extend this product to infinity. And they want us to show that this infinite product let's just write m equals infinity. Fails to be a rational function. I noticed that the total power of t in the denominator is infinite, and I believe that makes that makes it go faster towards 0 at infinity than any rational function will do. And I thought a little about it, and if we have a rational function, then there's some integral power of t. So when that is multiplied by the rational function, then we'll have a non-zero, non-infinite limit as t tends to infinity. And I believe that if it is an algebraic function, then we'll have some rational power of t where that holds, so that when we multiply the function with any rational power of t, then the function will either diverge or tend to infinity or not for all of them. And that's the case with this infinite product. Whichever power of t we multiply, then the degree of the new denominator will be larger, so that the limit will be naught as t tends to infinity. Therefore, it's not a rational function, and I believe for the same reason it's not an algebraic function either. So it's a transcendental function.